In the previous lecture, we were discussing about a general theorem that can enable us to calculate the lift and the drag force because of a potential flow around a closed contour, and that theorem is known as Blasius force theorem. So, we will try to derive the Blasius force theorem and see that for the special case of flow past a circular cylinder with rotation, how can you use the Blasius force theorem to calculate the lift and the drag force. So, let us say that you have an arbitrary shaped body like this, any arbitrary shaped body, and you have a potential flow past this. So, you can take a small element dl and on that small element dl you have a pressure P which is perpendicular to dl. Let us say that this pressure P makes an angle alpha with the horizontal line along which this incipient flow is taking place. U infinity is coming from the first stream. So, now if you consider this dl, dl will have its components say dx along x and dy along y. Okay. And this is the direction of P. So, we can construct a vector P like this arbitrarily with an angle say alpha with dx. So, what is the horizontal component of this force? dFd, the horizontal component is the drag force and vertical component is the lift force. So, if this is the P, then horizontal component is minus P cos alpha into dl, right. Why minus? Because the P is in this way, so horizontal component is along the negative direction of u infinity, and dFl, what is that? P sin alpha into dl. So, dl cos alpha is, so this angle is, if this angle is alpha, then this is 90 degree minus alpha. So, this is alpha, right. So, dl cos alpha is nothing but dy. And dl sin alpha is nothing but dx, right. Okay. Now, if you calculate dFd minus I into dFl. So, you form a complex quantity in which you absorb both the drag force and the lift force. So, minus P dy minus IP dx. So, minus IP right. because these two minus cancel and I square is minus 1, right. So, this is the complex conjugate of dz. dz is dx plus I dy, its complex conjugate is dx minus I dy. So, this is dz star, let us say, complex conjugate of dz. Remember, we have taken an arbitrary shaped body, not necessarily a circular cylinder. So, now let us use this part of the board maybe. So, the contoured integral of dfd minus I dfl Now, as we wrote for the problem of flow past a circular cylinder, in general, assuming those assumptions are valid, we can write p plus half rho p infinity plus half rho u infinity square is equal to p plus half rho v square, right. V square is nothing but small u square plus small v square. So, this is u plus I v into u minus I v. Okay. So, from here in this equation we will substitute this p from here. So, minus of contour integral of I, p is p infinity plus half rho u infinity square minus half rho u plus I v into u minus I v, this into dz star. One obvious thing is that the integration of p infinity plus half rho u infinity square, which is a constant over a closed contour, is 0, right. It is physically felt by, if you have a uniform pressure distribution around a closed body, the net force because of the uniform pressure distribution is 0. So, this part will not contribute to the integration. So, you can write I rho by 2, this minus and minus makes it plus, u plus I v into u minus I v into dx minus I dy. Okay. Now, u plus I v into dx minus I dy, if you make this calculation, this is u dx minus u I dy plus v I dx, then I square is minus 1. So, minus 1 into minus 1 is v dy. So, u dx plus v dy minus, so plus I into v dx minus u dy. Can you tell what is the value of this on the surface of a body? Surface of a body is a streamline, and streamline is defined by the equation dx by u equal to dy by v, right. So, dx by u is equal to dy by v is a streamline. Therefore, v dx minus u dy, this is equal to 0. Just for the sake of interest, calculate u minus I v into dx plus I dy. So, it is u dx plus u I dy minus v I dx then plus v dy. So, u dx plus v dy plus I into u dy minus v dx, this is 0. Therefore, on a streamline these two are the same. Hence, we can replace u plus I v into dx minus I dy with u minus I v into dx plus I dy. Therefore, this becomes I rho by 2, this is u minus I v whole square into dx plus I dy, right. So, just to help you to follow, we have replaced u plus I v into dx minus I dy with u minus I v into dx plus I dy. Therefore, the net result is the following. So, f d minus I f l is equal to I rho by 2 contour integral u minus I v is what? df dz. So, if you know the complex potential, just by using the derivative of the complex potential you can calculate the lift and the drag force simultaneously. This is the power of this complex analysis. So, this is called as Blasius force theorem. So, let us illustrate the use of this theorem through the example of flow past a circular cylinder with circulation or with rotation. Okay. So, in that case what is f? U infinity z plus m is u infinity r square, right, u infinity r square by z minus I gamma by 2 pi ln z plus a plus I b. So, what is df dz? U infinity minus u infinity r by z square minus I gamma by 2 pi z. U infinity r square by z square, right. Okay. So, df dz whole square is a plus b plus c whole square. So, let us write that u infinity square plus u infinity square r to the power 4 by z to the power 4 plus I square gamma square by 4 pi square z square a square plus b square plus c square plus 2ab. So, minus 2 u infinity square r square by z square plus 2bc plus 2 u infinity I gamma by I gamma r square by 2 pi z cube minus 2 ac. So, minus 2 u infinity I gamma by 2 pi z, right. So, you can see that this df dz is a complex number which can be represented as a power series of z. So, in general this is the scenario for a function which is an arbitrary function, complex function. So, we can write, so let us say the function is c, say f z is equal to c minus 2 into z minus. So, let us start with from the extreme negative coefficient to an extreme positive coefficient. We will write some intermediate coefficients like c minus 2 z minus a to the power minus 2 plus c minus 1 z minus a to the power minus 1 plus c 0 into z minus a to the power 0 which is 1 plus c 1 into z minus a to the power 1 plus c 2 into z minus a to the power 2. In this way it also goes from this side an extreme term to this side an extreme term. So, this is also called as Laurent series, a way of writing a series expansion of a complex function. So, this is very similar to this with a equal to 0. Interestingly, this function is singular at z is equal to a, right, and z is equal to a is called as a point of singularity because it is 1 by z minus a. So, at z is equal to a it will be 1 by 0 type of thing. So, z is equal to a is a point of singularity. So, if this function here the point of singularity is z equal to 0, a equal to 0. Okay. So, for that purpose let us think of calculating the integration of dz by z. Okay. So, z is equal to r e to the power I theta. So, dz, so here we are calculating it on the surface of a cylinder, that means small r equal to capital R and you are varying theta. So, we can write this as capital R. So, dz is equal to r I e to the power I theta d theta. Okay. So, you can write this in this case dz is r I e to the power I theta d theta by z itself is r e to the power I theta. Theta is how much? From 0 to 2 pi. So, everything gets cancelled. So, this becomes 2 pi I. So, we can generalize this by saying that if there is a coefficient C0 here, then integral of this over z will be 2 pi I into C 0. This is called as residue theorem. Although it is considered as a theorem, but it is very intuitive and easy to derive.
2 pi C minus 1 I think.
Yes, 2 pi sorry, C minus 1, not C 0, C minus 1, right. So, this integration is 2 pi I that multiplied by C minus 1. So, using that theorem and all other terms will be 0. How you can show it? Very easily. You calculate dz by z to the power n, okay. Other than n equal to 1, you will see that all other integrals will be non-existent. So, what will matter is the coefficient of 1 by z here. So, what is the coefficient of 1 by z? This one. So, what is the Fd minus IFL I rho by 2, this for a circular cylinder it will be this into 2 pi I into the coefficient this one minus 2 u infinity I by 2 pi, into gamma, right. So, let us see what are the things which cancel, this 2 pi cancel, this 2 cancel, I square is minus 1. So, this becomes I rho u infinity gamma. So, if you compare this with the right hand side, you will see that the drag force is still 0, but the lift force is minus rho u infinity gamma, right. So, this is known as Kutta-Zhukovsky theorem. So, this is the lift force and you can see very nicely, you can up to this extent you can calculate lift force on any shape, and this is of course for a special case of flow past a circular cylinder, but it can give you a very nice overview of what is the physics of the lift force. You can clearly see that if gamma is clockwise, if gamma is anti-clockwise, then FL is negative. If gamma is negative, that is if it is clockwise rotation, then FL is positive. That means if there is a object which is rotating in a clockwise fashion, it will experience a lift force upwards. If it is rotating in an anti-clockwise direction, it will be a negative lift force, it will be experiencing a force downwards. So, we have understood at least in principle how to model flow past an object of a circular shape and how to find out the lift force and the drag force. Question is, in reality all objects are not circular cylinders, right. So, if you have an object which is of a different shape, how do you use the result of the flow past a circular cylinder to extrapolate that to the situation of flow past something which is of a more complex shape and perhaps a shape which is more interested for aerodynamic calculations. For that, what we use is something called as conformal mapping. So, I will give you a little bit of introduction on what is conformal mapping and an example of that. So, conformal mapping in principle is nothing but a mapping of an analytic function from one complex plane to another complex plane. So, I give you an example of a conformal mapping. The objective is pretty clear that from a circular shape you want to map to a shape which is perhaps deviating from circular, but more practically relevant. So, there is a complex plane which is say zeta. From there you transform to a complex plane which is z. So, which you call as zeta plus b square by zeta. Okay. So, let us consider that in zeta plane you have a circle of, consider a circle of radius b. So, in that case zeta will be b into e to the power I theta, right, r e to the power I theta, r is equal to b, which is fixed. So, z will be beta e to the power I theta, sorry, b e to the power I theta plus b square by b. So, b e to the power minus I theta. Okay. So, b cos theta plus I sin theta plus b into cos theta minus I sin theta. So, 2b cos theta so this is 2b cos theta, right. So, now you take the x axis. So, when theta equal to 0, what is the corresponding z? Z is 2b, right, which is basically only real component, there is no imaginary component. So, this is say 2b. When theta is 2 pi, then it is minus 2b, right. So, if this is 0, this is minus 2b. Yes. So, when theta is pi, this is minus 2b. So, you can see that the transformation transforms the circle to a slender piece like this. Okay. So, this is the beauty of this conformal mapping. So, if you now want to understand the flow past a slender piece like this, you can model that as a flow past a circular cylinder of radius b in the zeta plane and then apply a transformation where the zeta is transformed into z. I will give you another example before we call it a day. So, example 2, you have a, the radius of the circle A is greater than b. Here we have considered the radius is equal to this special b, but if the radius A is greater than b, so zeta is equal to b, sorry, a e to the power I theta. So, z is equal to a e to the power I theta plus b square by a e to the power minus I theta, right. So, a into cos theta plus I sin theta plus b square by a into cos theta minus I sin theta. So, what is x? A plus b square by a cos theta and y is a minus b square by a sin theta, right. You can eliminate theta by noting that cos square theta plus sin square theta equal to 1, therefore, x square by a plus b square by a whole square plus y square by a minus b square by a whole square is equal to 1. So, this represents an ellipse, right. So, by this mapping you can first calculate the flow past a circular cylinder and then apply this conformal mapping to predict the flow behavior past an elliptic cylinder. So, in this way this is such a beautiful transformation that using this kind of transformation by choosing different values of the radius of the circle you can actually transform the flow past a circular cylinder to a flow past an object which apparently is very much different in shape as compared to a circular cylinder. So, that is why flow past a circular cylinder is so fundamental, that once you have a clear idea of flow past a circular cylinder you can apply a transformation and analyze problems of more complex geometries. So, to summarize, we have discussed about various aspects of potential flow, starting from simple elementary flows. We have constructed flow past a circular cylinder. With rotation we have seen how to calculate the lift and the drag force, and then finally how to generate bodies of more complex shapes from the consideration of circular cylinder or a circle in one particular plane by using conformal mapping. Thank you very much. We will start with a different topic in the next lecture. Thank you.